In this video, we will talk about sensor networks and manufacturing services. Advanced sensing leads to big data populated in ERP, MES, and PCS. Currently, significant amount of data already exists in the manufacturing domain, but are not fully utilized for real-time process monitoring, fault diagnosis, and performance optimization. Realizing the full potential of MES and advanced sensing depends on the development of new methodologies to extract useful features and patterns from the data, and then exploit the new knowledge to enable drone manufacturing. Here, we categorize sensor-based manufacturing informatics and control into four specific areas as below. First, data representation and visualization. Sensing systems communicate data in real time with databases. In many cases, energy budget and bandwidth pose significant challenges on the efficiency and effectiveness of data transmission. As such, a compact representation of data is necessary. A compact representation gets rid of the need to store large amount of raw data. For instance, store significant Fourier or Wirick coefficient for compression and transmission purposes. This compact representation also makes the underlying pattern more prominent in the transformed domain, so that the extraction of salient features becomes much easier in the context of smart manufacturing. Also, data visualization is critical to presenting key information and patterns to end users in an easily comprehensible way. Network visualization is also conducive to characterizing and representing the interconnected network of manufacturing links, thereby facilitating the formation of a virtual machine network in cyberspace. Pattern recognition and feature extraction. Data representation and visualization help transform the raw data into alternative domain. For example, frequent domain, wavelet domain, and state space domain. The next step is to learn and recognize hidden patterns using pattern recognition methods such as principal component analysis, data clustering, factor analysis, multilinear subspace learning, and Bayesian networks. Further, feature extraction focuses on the quantification of salient patterns as features for systems informatics and control. Sensor data fusion. It is common that multiple sensors with different sensitivity to certain operational characteristics are installed in a manufacturing system to collect homogeneous or heterogeneous signals. It may be noted that these multi-sensor signals can be interrelated if they are monitoring system dynamics from different perspectives. Multi-sensor data fusion consists of three critical steps. First, identifying multi-scale information flows among multiple sensors. 2. Modeling the dynamic evolution of the underlying process dynamics, and exploring the new knowledge from sensor fusion for system informatics and control. Conventionally, linear correlation structures between multiple sensors are characterized to monitor and control manufacturing processes. Effective multi-sensor fusion strategies should consider both information transfer flows in real time, sensor signals, and the evolution of non-linear dynamics in the underlying process. Process control and decision making. Once a manufacturing process is out of control, the next step is to take optimal action to bring the system back under control. The action plan depends on a number of steps such as root cause diagnostics, condition prognostics, and system optimization. Traditional methods for root cause diagnostics include engineering-driven statistical models, operating models, and effect analysis. Also, physics-driven models can be formulated based on specific failure mechanisms in the manufacturing system. However, they are often not able to match the real data very well and are therefore inadequate to predict system malfunctions and identify root causes. Data-driven models leverage the real-time sensor signals to characterize and model degradation behaviors in the underlying process. A salient advantage is the ability to transform high-dimensional sensor signals into low-dimensional degradation features. For condition prognostics. Furthermore, simulation modeling replicates a real-world manufacturing system and better explains the underlying mechanism of the system. Hence, simulation modeling is widely used for diagnostics, prognostic, and optimization purposes. In addition, simulation optimization can be integrated with the wealth of sensor data for manufacturing process modeling and decision support. Now let's look at the IoT manufacturing applications. Figure 5 shows Google Trends comparison of the popularity levels of cloud manufacturing, Industrial Internet of Things, in these 7 years. In this section, we'll present an overview and review of IoT manufacturing applications in the following categories. The first category is IoT-based cloud manufacturing. IoT feels increasing interest to design and develop new system infrastructures that investigate wireless sensor network and cloud computing into manufacturing settings. We listed some examples here. Internet-based data flow and cloud database in the IoT context effectively facilitate mutual interaction between humans and machines. Cloud computing and analytics can help resolve complex decision-making problems in manufacturing. Cyber-physical manufacturing systems. The term cyber-physical manufacturing is also used in the literature to show the interrelated technologies of IoT, manufacturing, and cyber-physical systems. Cyber-physical systems integrate sensing, computation, control, and networking into physical objects and infrastructure, connecting them to the internet and to each other. We listed 2 examples here, and here we have more examples. Energy efficient management. IoT is also utilized for the optimal management of energy efficiency in manufacturing. We listed 2 examples here and 2 more here. Manufacturing operations management. We listed 5 examples here. Another category of IoT application is safety and ergonomics. There are so many research that focus on the design of IoT systems for safety and ergonomics in the manufacturing industry. Ergonomics, in other words, we can call it human factors. Basically, it studies how human beings can perform better in the working environment. For example, so now when you try to open a door, so how do we determine the height of the door handle, right? And also, how do we determine the height of your seat if it is adjustable? So those are the topics of early studies in human factor or ergonomics. But if people are to operate complex systems, so definitely there will be more topics need to be studied so that people and the technology can interact in a more safe and effective way. Supply chain and logistics. Physical internet is an IoT-related concept proposed in the domain of manufacturing, supply chain, and logistics. So here are some representative studies in this direction. In addition to the academic research, industrial organizations have increasingly invested in new IoT technologies for process monitoring, operation optimization, fault detection, and optimal control. Table 3 shows a representative list of companies that implement IoT solutions in industrial case studies. Note that most of the examples are for marketing purposes, and more research is urgently needed for IoT system optimization, data modeling, and cybersecurity, and so on.